So now let's look at a second type of simplex problem, and that's one where we are minimizing. So we are in standard form if we're minimizing an objective function subject to a set of constraints, but notice that this set of constraints has a greater than or equal to sign for every single one of them. So this is different than the standard form for a maximizing. With maximizing, each one of these had a less than or equal to. But if we want to minimize, then we're going to have a set that's going to be greater than or equal to. So this is a second type of simplex. There's also a simplex where you're going to have mixed constraints. We're not going to go there in this class. Like we said before, we are just touching the surface on what linear programming is and just looking at a couple of basic types. There are entire classes built around this idea in mathematics. There are entire branches devoted to it. But I do want to look at the second type of form, standard form, and that's for a minimization problem. So basically the idea here is that we're going to convert this into a maximization problem. And then we're going to be able to apply the simplex method to it. So how do we go about converting this? Well, what we're going to do is we're going to form an augmented matrix for the system of inequalities, and we're going to add a bottom row consisting of the coefficients of the objective function, and then we're going to transpose that. And when we transpose that, that creates what's called a dual maximization problem that corresponds to that matrix. And then we're going to apply the simplex method to that dual problem, and that's going to give us the solution to the original problem. Now, I'm not going to go through and prove any of these theorems. Like I said, we're touching the surface on this stuff, but this theorem is called the von Neumann duality principle in linear programming. Just in case you want to Google. So let's look at a couple of examples. The first one's just going to be a problem that's kind of set up. Second one, we'll do a word problem. So we want to minimize w equals 3x1 plus 2x2 subject to the constraints 2x1 plus x2 is greater than or equal to 6, x1 plus x2 is greater than or equal to 4. Notice this is in 2 dimensions. We're limiting it to the first quadrant. This is almost always going to be a statement in these problems. So we've got x1s and we've got x2s here. So let's create a matrix with this. So we're going to put the constraints in first. We have 2x1 plus x2 is greater than or equal to 6. x1 plus x2 is greater than or equal to 4. And then we're going to put 3 and 2. Now we're putting the coefficients in for that objective function. And that's going to end up being equal to 0. And we're going to transpose this, and that's going to create, it's going to give us the coefficients, rather, for that dual program, or that dual problem. So I'm viewing it like that. So let's write out that dual problem. Remember, in the dual problem, this guy is going to be the objective. We are going to maximize z equals 6x1 plus 4x2. Actually, I'm going to call them y's. Subject to the constraints 2y1 plus y2 is less than or equal to 3. And y1 plus y2 is less than or equal to 2. So there's your y1 plus 2y1 plus y2 is less than or equal to 3. Here's your y1 plus y2 is less than or equal to 2. Those are the constraints. Objective is always on the bottom. This is 6y1 plus 4y2 is equal to 0. Oh, sorry, is equal to z. No, I'm using y's here instead of x's because this, we want to remember that this variable is for the dual problem. It does not tell us what that is. But we'll talk about how to get that answer in just a minute. So now we've got a problem that's in a standard form that we know how to solve. Let's solve it. So we're going to move everything to one side here, keeping z positive. Oh, that's supposed to be a plus. Remember, this is a positive 4 here. We're going to introduce slacks into the constraints. So now let's write out our first table. So we've got y1, right here, y1, y2, s1, s2, and z as variables. So we've got, for the first constraint, 2y1 plus 1y2 0 plus 1s1 plus 0s2 plus 0z is equal to 3. And then we're going to have 1, 1, 0, 1, 0, 2 for that second line. And then putting this guy in, -6, -4, 0, 0, 1, and 0. So the most negative number here is the -6. We're going to look at ratios. So 2 over 1, if I take this divided by that. 3 over 2. So that's 1/2, that's the smallest. So there's where we're going to pivot. So row 1 is going to be 1/2 row 1. Still pivoting here. So let's take row 2 and replace it with row 2 plus -1 times row 1, and take row 3 and replace it with row 3 plus 6 times row 1. So we're going to have -6 plus 6 is 0. -4 plus 3 is -1. 0 plus 3. 0 plus 0. 1 plus 0. And 0 plus 6 times 3 over 2, which is 9. So let's go through the process again since we have a negative here. We're going to have 1/2 divided by 1/2, which is 1. 3/2 divided by 1/2 is 3. We are pivoting here. Turn that guy into a 1 by replacing row 2 with 2 times row 2. Remember, we're pivoting here. So I'm going to come up here to do this. We're going to replace row 1 with row 1 plus 1/2 negative 1/2 times row 2. And then row 3 is it's going to be row 3 plus row 2. Row 2 stays the same. Row 3 is going to be just row 3 plus row 2, so I'm going to go ahead and do that one first. And then row 1 is row 1 plus negative 1/2 row 2. So there's our final table, but this is going to read a little bit differently than what we're used to. Usually we say we look for those identity columns from like an identity matrix. That's not how we read this when we do a minimization problem and we've now created a dual problem. The solutions are actually going to correspond to where those slack variables are. So this is going to be your solution for x1. This is your solution for x2. Now your z is still going to be in the same place. So this guy is minimized. When x1 is equal to 2 and x2 is equal to 2. And then the minimum value is going to be 10. So the process is the same, but that final solution is going to be just a hair different in how we interpret that. So now let's take a minute and let's look at a word problem. So let's read through this one together. A small petroleum company owns 2 refineries. Refinery 1 costs $20,000 per day to operate, and it can produce 400 barrels of high-grade oil, 300 barrels of medium-grade, and 200 barrels of low-grade oil each day. Refinery 2 is newer and more modern. It costs $25,000 per day to operate, and it can produce 300 barrels of high-grade oil. This is a day. 400 barrels of medium-grade oil per day, and 500 barrels of low-grade oil each day. The company has orders totaling 25,000 barrels of high-grade oil, 27,000 barrels of medium-grade oil, and 3,000 barrels of low-grade oil. How many days should it run each refinery to minimize its costs and still refine enough oil to meet its orders? So here what we're trying to do is minimize the cost. Now, we could run each refinery theoretically, an infinite number of days. Now, that doesn't make a whole lot of sense in the context of the problems, but we could run it 100 days or 200 days, but do we really need that much? How much do we have to run each? We want to minimize the cost for this company, but we want to produce the oil that we need to in order to fill this order. So let's create a few variables. Let's let X1 be the number of days for refinery 1. And then let X2 be the number of days for refinery 2. So our goal here is to minimize the objective, and I'm going to use W here. We want to minimize our cost. Well, it's going to cost us $20,000 a day for refinery 1 and $25,000 a day for refinery 2. And then we need to come up with some constraints. And the constraints are going to be how much oil in terms of high grade, medium grade, and low grade each refinery can produce a day. So refinery 1 can do 400 barrels of high grade oil. Refinery 2 can produce 300 barrels of high grade oil. And we're going to need a total of 25,000 barrels of high grade. Refinery 1 can produce 300 barrels of medium. Refinery 2 can produce 400 of medium. And we need 27,000. So we could produce more than 27,000 barrels of medium grade. That would be fun, but we got to at least produce 27,000 or we're not going to be able to fill this order for the company. So that's the idea. That's why we're using greater than or equal to here. And then 200 barrels of low grade for refinery 1. 500 of low grade for refinery 2. And that's got to be greater than or equal to the 30,000 that we have an order for. So remember, this is for high grade, this is for medium grade, and this is for low grade. So it kind of goes without saying, but I'm going to write it anyway. X1 and X2 represents the number of days each refinery is running. Obviously, it can't be equal to 0. Oh, sorry, it can't be less than 0, so it's going to be greater than or equal to 0. So let's set this up in a matrix. Remember, we've got X1s and X2s in here. So we're going to put our constraints in first. And then the objective goes on the bottom. And we want the transpose. So we're kind of viewing this guy this way. And if we transpose that, we're now viewing that this way. So then let's write out what our dual problem says. The dual problem says we are going to maximize the objective. 25,000 Y1 plus 27,000 Y2 plus 30,000 Y3. Subject to two constraints. 400 Y1 plus 300 Y2 plus 200 y3 has to be less than or equal to 20,000. And 300 y1 plus 400 y2 plus 500 y3 is less than or equal to 25,000. So there's our dual. Now, let's rewrite everything. Moving everything to one side. Keeping z positive, so that's now equal to 0. And for the second and third, we need to introduce slacks. So let's set up our table. We have y1, y2, y3, s1, and s2, and z. Make sure you watch your zeros there. That is 20,000 on the end. These numbers are kind of big. So remember, this table, we can't read it the same way as we did the maximizing tables that were with a problem that was from standard form. Our final answer will actually end up being in these two columns. But the process is going to be the same. Find the most negative number in the bottom. The most negative number, that smallest negative, is that guy. Now we've got to look at ratios. So let's look at this 25,000 and then let's divide it by 500. And now let's look at this 20,000 and divide it by 200. Remember, it's this guy divided by that guy. Which number's smaller? 50 smaller. So now we're pivoting here. So now we need to multiply by row 2 by 1 over 500. So row 2 is going to be 1 over 500 times row 2. I'm setting my table up. The other two rows are going to stay the same, so I'm going to go ahead and copy down row 1. So this is going to be 3 over 5, 4 over 5, 1, 0, 1 over 5, 100, 0, and 50. That bottom row stays the same. Remember, we are pivoting here. And I'm going to copy this table to the next page, so we'll have it for the next step. So now we need to take row 1 and replace it with row 1 plus negative 200 times row 2. And replace row 3 with row 3 plus 30,000 times row 2. Row 2 stays the same, so I'm going to go ahead and copy it. So if I take row 1 and replace it with row 1 plus a negative 200 times row 2, that's going to zero this guy out in the Y3 column. And when I plugged everything into my calculator, I got 280, 140. We already knew that was a 0. This is a 1. Negative 2 over 5. 0. And 10,000. When I take row 3 and replace it with row 3 plus 30,000 times row 2, we know that that's going to be a 0. Plugging everything in the calculator. So there we are. So now we need to look at, do we pivot again? We do have negatives in the bottom. The most negative number, the smallest negative, is that one. So let's figure out where we're going to pivot. So we're going to take this 50 and we're going to divide it by 3 over 5. It's a ratio of this over this. That's about 83. And then a ratio of this over this. So 10,000 divided by 280 is about 35. 35 is the smallest. This is where I'm pivoting. So I'm going to take row 1 and multiply it by 1 over 280 times row 1. Everything else stay the same for now. And then we're going to do some Gaussian elimination. Remember, we're pivoting there. So now we're going to take row 2 and replace it with row 2 plus negative 3 over 5 times row 1. And row 3 is going to be row 3 plus 7,000 row 1. So row 1 is going to stay the same. I'm just going to copy. So row 2 minus 3/5 R2. And then take row 3 and add 7,000 row 1. Okay, notice we do not have any other negatives in the bottom, so this is the final table. And since this was a dual problem, the solutions are going to be here for x1 and here for x2. With the dual problem, your solutions will show up in the slack variable columns. And this is our objective. That's going to be our minimum cost. So we need to operate refinery 1 for 25 days. And refinery 2 for 50. The minimum cost is going to be $1.75 million. So now if we wanted to figure out, are we going to produce more than what we need, we can by using these values in the original equations. So just for fun, I'm going to go recopy those original equations. Well, copy. So remember, these were the original equations. So let's look at how much we're producing for the high, the medium, and the low grade. So this is where we're going to substitute in for refinery 1. Remember, that was our X1, 25, and refinery 2, that was our X2 for 50. And we're going into those constraints. So we have 400 times 25 plus 300 times 50. And that's going to equal 25,000. So we're producing exactly 25,000 barrels of high-grade oil. We're going to have, in that medium grade equation, 300 times 25 plus 400 times 50. So that's going to give us 27,500. So remember, we needed at least 27,000. We're producing 500 extra barrels of medium grade oil. And then for low grade, 200 times 25 plus 500 times 50. And that's going to be 30,000. And that's exactly how much we needed there. So by looking at this dual problem, we have discovered that we're going to have to run refinery 1 for 25 days and refinery 2 for 50 days. But we're going to end up with an extra 500 barrels of medium grade oil. So we can figure out how much excess we have by going back to those original equations and plugging that solution in. So that's how you do a minimizing problem in Simplex that's written in standard form. And like I said before, this is just touching the surface of linear programming, just looking at a couple of different cases. There are cases on how to do this, and algorithms for mixed constraints and stuff like that, which you would see in a linear programming class. But this is a great application, especially for the Gaussian elimination.